have you ever stopped to think about what makes a great app, well, great? What's the real difference between software that feels amazing and software that's just frustrating? A lot of the time, it comes down to two big ideas: how it handles errors when things go wrong, and how it juggles a bunch of tasks at once. Today, we're diving into Java's power tools for making software both stable and fast, exceptions and threads.
Oh man, we've all been there, right? You're right in the middle of something important. Maybe you're about to make a payment, or you're in the zone playing a game, and bam, the app just closes. Or worse, it just freezes on the screen, totally unresponsive. That feeling, that exact problem, is what we're going to unpack today.
So at the end of the day, almost every application is fighting two massive battles. First, what in the world do you do when something completely unexpected happens? And second, how do you manage really slow, time-consuming tasks without making the entire app grind to a halt?
You see, good software doesn't just cross its fingers and hope everything works. No way. It has a built-in game plan for when things go south. As you can see here, the idea is to anticipate problems. When one happens, the program creates a special signal. We call it an exception. And then it throws that signal, kind of like a flare. And a different part of the code is built specifically to handle it, to catch that flare and deal with the problem without a total meltdown.
And that brings us to our first superstar tool, exception handling. I want you to think of this as the ultimate safety net for your code. It's the system that's always there, ready to catch your program when it stumbles, preventing a small slip from becoming a catastrophic fall.
Okay, so how does this actually work in the code? Well, it all kicks off with something called a try block. This is basically you telling Java, hey, listen up, the code I'm about to run, it's a little risky. It might fail. This is where you put anything that's a bit unpredictable, like connecting to a website or processing a file someone uploaded. It's your official danger zone.
But what happens if disaster does strike inside that danger zone? That's where the catch block swoops in to save the day. Think of it as your program's plan B. It's designed to catch a very specific kind of error. So instead of crashing, it runs a different set of code, maybe showing the user a friendly message like, oops, invalid card details, please try again.
And then you've got the finally block. Now, this one is super important because it's the part that runs no matter what. Whether the try block worked perfectly or the catch block had to jump in, the finally code will always execute. It's perfect for essential cleanup tasks, like closing a database connection to make sure you don't leave things a mess.
So, you might be wondering, how does Java even keep track of all the things that can go wrong? Well, it's all organized like a family tree. At the very top, you have a class called throwable. Everything bad that can happen stems from this. It then splits into two main branches: errors, which are usually catastrophic system failures you can't do much about, and exceptions, which are the problems our code is actually designed to catch and handle.
And inside that exceptions family, things get even more interesting. There are basically two main flavors. First, you have checked exceptions. The Java compiler literally checks your code and forces you to handle them. Think of trying to read a file that might not exist. You have to have a plan for that. Then you have unchecked exceptions. These usually point to a bug in your code, like trying to divide a number by 0. The compiler won't warn you, but they'll still crash your app if you're not careful.
All right, so we've built a bulletproof app. It doesn't crash. Awesome. But what if it's slow, like painfully slow? Now we're going to tackle that second huge challenge: how to keep our apps feeling snappy and responsive even when they're doing some heavy lifting in the background.
The secret weapon here is something called a thread. And honestly, the best way to think about it is like this. Your whole program is a company. A single thread is like one employee at that company. It's a single path of execution, one worker, focused on doing one job at a time, and it shares the company's resources, like memory, with all the other employees.
So why would you want more than one employee? Isn't one enough? Let me give you a perfect example. A music app. You've got one thread that's busy playing the song you're listening to right now. If that was your only thread, the entire app, the user interface, everything would freeze solid while it tried to download the next song on your playlist. But if you hire a second thread just for downloading, the music never stops and you can still skip tracks and browse your library. That's the magic of multithreading.
And a thread actually has its own little life cycle, a whole journey it goes on. It starts out as new the moment it's created. Once you give it a job, it becomes runnable, basically standing in line waiting for the computer's processor. Once it gets its turn, it's running. Sometimes it might have to pause and go into a waiting state, and then once its job is totally done, it enters the dead state.
Now, if you want to hire these new employees, you've basically got two ways to do it in Java.
You can either extend the thread class or implement something called the runnable interface. Both will get the job done, but the pros will tell you that implementing runnable is almost always the better choice. Why? It's simple, really. A class in Java can only extend one other class. If you extend thread, you've used up your one shot. By implementing runnable instead, you keep your options open, making your code way more flexible down the road.
Okay, so our office is buzzing with activity now. We've got multiple threads, our employees, all working hard. This is great for getting stuff done fast. But it also introduces a brand new, kind of scary problem. With everyone running around at once, how do we keep them from stepping on each other's toes and causing total chaos?
This right here, this is the classic example that explains everything. Just imagine two people, or in our case, two threads, trying to pull cash from the same bank account at the exact same microsecond. Thread A reads the balance as $100. Thread B reads the balance as $100. Thread A subtracts 50 and writes back 50. Then thread B subtracts 20 and writes back 80. The final balance is wrong. That, my friends, is a race condition, and it's a huge source of bugs in multi-threaded programs.
So that little piece of code, the part that's actually touching the shared bank account balance, that has a special name. We call it the critical section. It's the danger zone, the sensitive area of our program that we absolutely must protect to make sure only one thread can be inside it at any given time.
So how do we protect it? The answer is a concept called synchronization. And honestly, it's just like putting a lock on an office door. In Java, every single object has a built-in lock, called a monitor. Before a thread can enter that critical section, it has to get the key and lock the door. As long as it's inside, no other thread can get in. They all have to line up and wait outside until the first thread is done and unlocks the door.
Okay, so keeping threads from crashing into each other is one thing, but what happens when they actually need to work together? This brings us to a classic computer science problem called the producer-consumer problem. Just think of a chef in a kitchen. That's our producer thread, making dishes. And then you have a waiter. That's our consumer thread, delivering those dishes. They need to coordinate, right? The waiter can't deliver an empty plate.
This is where Java gives us some really cool tools. The first one is called wait. When a thread calls wait, it does two things that are super important. First, it releases the lock it was holding, opening up the kitchen for someone else. Second, it goes to sleep. It's the consumer thread saying, you know what, there are no dishes for me to pick up, so I'm going to take a nap and let the chef work.
All right, so our consumer thread is asleep. How do we wake it up when there's work to be done? Well, once the producer, our chef, has a new dish ready, it calls a different method, notify. This acts like a little tap on the shoulder. It wakes up just one of the threads that was sleeping, basically saying, hey, wake up, your order's ready.
And then there's its sibling, notify all. And yeah, it does exactly what it sounds like. Instead of waking up just one thread, it wakes up every single thread that's waiting. They all wake up and then have to compete to see who gets the lock first. In more complicated situations, this is often a much safer bet because you don't risk leaving the one thread you really needed to wake up still asleep.
All right, let's take a step back and look at the big picture here. What we've really been talking about are the two fundamental pillars that hold up almost every piece of modern, high-quality software. On one side, you have this robust, defensive system for making sure your app doesn't fall apart when things go wrong. And on the other, you have this powerful system for making it fast, efficient, and responsive.
So I want to leave you with this one final thought. If exception handling is the unbreakable shield that protects your app from disaster, and multithreading is the high-performance engine that makes it fly, how does that change the way you look at the apps you tap on every single day? Next time something works seamlessly, you'll know a little more about the silent heroes working behind the scenes. Thanks for joining this explainer.